Have you finished the worksheet? From yeah, I know more. Okay, let's see worksheet on that one. Ionic bond and covalent bond. Okay, so I want to check with you one of the answers to one of those questions. Yeah, let me forward this one. Yeah. Oh, okay, great. So maybe let's try the question on CO2 first. Carbon dioxide, okay, and then we'll use this to do a review. Yes. Oh, you do it. I'll bring you one later. So let's take a look at how carbon dioxide, the molecule carbon dioxide forms. Okay, so we have in here from last time. This is how the water molecule H2O forms. Okay, so how does a stable, remember the color screen indicates stability. So how does a stable H2O molecule form? Okay, so how does it form? You have on the right what we call an H2O molecule, okay, or a H2O molecule here. On the left, you have a bunch of unstable atoms. Okay, so this is a stable H2O molecule on the right, and these are the unstable H and O atoms. Remember, atoms they won't become stable. Okay, and this is not just for H2O, but for any other molecule. Okay, for that matter. So you have unstable H and O atoms. Now, for those of you who haven't finished the worksheet, okay, we'll work on this together. What about carbon dioxide? So how does a stable carbon dioxide molecule form? Well, first, we need to figure out the atomic number and also the electron arrangement of carbon and oxygen. So can anyone tell me if the atomic number of carbon is 6 and the atomic number of oxygen is 8, what the electronic arrangement are for C and O? What is the electron arrangement of C? How do we break down 6 electrons into electronic arrangement? We say it's 2, 2, 4, and for oxygen it's 2, 2, 6. Yeah, so 2, 4 and 2, 6. Okay, so this is clear, right? Break down 2, 4 and 2, 6. And we should only show, remember this? Okay, so if you were not here in the last lesson, remember in covalent bonding, when we draw covalent bonds, we only show the outermost shell electrons. Okay, this is why we need to break down the electrons into these electron arrangements and then just write out the last number in here. Okay, so let's draw carbon and let's draw one more oxygen on the side. So draw one more oxygen on the side, so we have a carbon in here. So it is unstable because it has only 4 electrons in the outermost shell. So we draw 1, 2, 3, 4. Doesn't matter where you put them. You can put them at 12 p.m., 3 p.m., 6 p.m., 9 p.m. position, doesn't matter. But we tend to group electrons 2 as a pair. Okay, 2 as a pair. And then we have oxygen here. Yeah, you can use dot electrons. Okay, for oxygen. Just make sure you use different symbols. Okay, so cross for one atom, dot for the other. If you have a third type of atom, you may use triangles. Okay, so you may use triangles. Now, how do we put together 1 carbon and 2 oxygen to make a stable molecule? So let's try. Is it by sharing just 1 electron? So let's explore our options here. So is it by sharing just 1 pair of electrons between the carbon and oxygen? Or is it by doing something else? So let me put this in here. As I want to show you that there's only one correct way of sharing electrons. Okay, so let me put down 3 different diagrams in here. There's only one correct diagram in here. So this does not happen. This does not happen. What is in between them? This happens. Okay, what is that? Okay, first, can you put down the symbols for carbon and oxygen in this diagram first? And can you try sharing 1 pair of electrons between atoms and tell me what you got? So if carbon decided to put one of these electrons here, how many cross electrons remain on carbon? So, okay, let's look at what we have there first. We have 4 crosses electron at the beginning. And then carbon, at this moment, it is using only 2 of the electrons in the bond length. How many cross electrons are there? 2. So we will draw 2 on the side. Yeah, you can put 1 on top, 1 at the bottom, but like I said, we like to group electrons together. Okay, so you can put them both on top, both at the bottom. Okay? But then, what about oxygen? If each of the oxygen has invested 1 of the dots electron, of the 6 dots electron in this covalent bond, how many dots electrons should be found on each oxygen? 5, right? 5, right? So can you draw 5 in here? And why am I using red? Why am I still using the color red? Yeah, because it's unstable. Let's count. Let's count the total number of electrons in the shell together. Look at this circle first. How many electrons do you count in just this circle? 7. 7 is not 8. Means it's not full. It's not stable. Okay? So this is why I still use the color red for this molecule. Okay? Showing that carbon dioxide does not have a single bond between carbon and oxygen. So let's try something else then. If carbon did not form a single bond, okay, what can it form then? So it can form a double bond by investing 2 of its electrons in each of the bond. But remember what sharing means, right? When I share something with you, I expect you to share something back, okay, in return. So therefore, when carbon shares 2 of its electrons, it expects oxygen to do the same. Okay, so therefore you see 2 dots electron and 2 crosses electron here. Are there any cross electron left on carbon? No. So we don't have to draw anything on the top or at the bottom of the carbon in here. But what about for oxygen? How many dots should I show on each oxygen? There were 6 at the beginning, but it's used to, so there are 4 left. Yes, okay. Keep track of the number of electrons. Okay? And you notice that I use the color green for this molecule. That's because it's stable. Okay, let's count again. We have 8 electrons in this circle. And not just in this circle, but in this circle as well, and in this circle. Do you see everybody is satisfied? Everybody is stable. Okay? And you may think, oh, if double bond makes it stable, what about a triple bond? Does this triple bond makes it even more stable? Well, unfortunately, this is not possible. Why? Because to form a triple bond, carbon has to donate or share 3 of its electrons to each oxygen, right? With each oxygen, but doesn't have that many to go around. So therefore, this is never an option. Okay? Can you figure out the whole? Can you write something? If you haven't been writing anything in the first lesson. Okay? So this is a, let me write this down. A stable CO2 molecule, and this should be your answer. But I mean, you should have done the homework. There's actually no homework. Okay, so I just ask you to check the answer. Okay, with the one you have on your worksheet. Okay, this is a stable CO2 molecule, and what we have on the left are a bunch of unstable C and O atoms. So remember, the take-home message, okay, for this page should be that atoms, they are not stable by themselves. But when they can partner up, you see a single hydrogen, a single oxygen, they are not stable because they do not have a full shell. However, they can partner up by forming covalent bonds. Sometimes it is a single bond, so you can see that this is a single bond. Sometimes it could be, they could be forming a double bond. Yeah, so can you convert this into an easy to read diagram? Okay, so we call these bonding electrons. So we call these also bonding electrons. But this diagram is a hassle to draw, which is why we will convert it into a diagram that looks like this. C with 2 O's on the side, and it will put 2 lines in between each pair of atoms. Those 2 lines represent a double bond. Okay? And when do you draw a single line, double line, or triple line? Well, it depends on how many pairs of electrons are shared. If you see 1 pair of electrons shared, it's a single one. So can you help me convert this diagram into the structural formula? So we call this structural formula. Okay, let's do this now. Okay, I'm going to write down the name of this thing. This is the structural formula, which shows the structure apparently. And this is the electron dot plot diagram. So pay attention to the wording electron Doppler diagram, they expect you to draw this. But then once you got the electron Doppler diagram, you can convert it or translate it into a structural formula like this. It's as simple as counting how many pairs of electrons. So put down a note and in here, maybe all of you can work on this together now. Convert this into a structural formula. Okay, how many lines should I draw between O and H? One. Yes, so therefore you can show just H, O, H, and then just draw a line in between. That's it. Yeah. I mean, if you have to make between these two, you will draw this any day, right? It's so much simpler, right? So this one is a structural formula. Just how we put down the notes like somewhere on the home, okay? When you convert electron dot cross diagram to into the structural formula. So into structural formula, we pay attention to the number of electron pairs. Okay, so remember each shared electron pair, okay, represents a bond. Okay, so each shared electron pair represents a bond. Where are the electron pairs? These ones. So this represents two pairs of electrons. Therefore, this represents two bonds, and therefore two lines. Okay, so two pairs of shared. You only count the electrons in the overlapping space, as those are shared. The electrons that are outside the overlapping space, they aren't shared. You don't count them. You only count the ones in the overlapping region. Okay? So put this down. Two pairs of shared electrons. Therefore, double bond, we say. And each shared electron pair represents a bond. Okay, so you can have as many as two bonds, one bond, or three bonds. Okay, so write down this conversion here. Number of electron pair bracket S shared, and what bond they correspond to. Okay, so type of bond. So we can have one pair, two pairs, three pairs, and it will be a single, double, and a triple bond, respectively. So far so good for me. Okay, so now they take me to anything that don't work. Okay, okay, that's what worked from last time. So can you write something? You should bring a notebook that is to class and not just sit there. Okay, right. So now that we understood covalent bond, we will look at some other aspects of ionic compound, which I forgot to mention. Okay, last time. So ionic compounds, so ionic compounds, additional properties. So first, we look at the color of ions. Okay, some ionic compounds, they contain colorful ions. Okay, but then there are some ionic compounds that are less, attractive. Okay, for example, sodium chloride. You know sodium chloride, when you dissolve it in water, do you see any particular color when you dissolve it in water? No, right? It forms a colorless solution. But some ionic compounds, they do, okay, have many different colors. They show a variety of colors. So some ionic compounds, such as NaCl, so such as NaCl, they are colored, they are white in solid state. Okay, so they are white in solid state. When they dissolve in water, they form colorless solution. So when they dissolve in H2O, they form colorless solution. You don't say the compound is colorless. The compound is white. Sodium chloride, the salt, is white. But when they dissolve, they form colorless solution. Okay? So how we put down this rule? White compounds, so white ionic compounds, whenever they dissolve, they don't form white solution. They form colorless solution. So you know this as a fact. Okay? And you can do an experiment on solving, right? Find out that white compounds, they dissolve to form colorless solution. some other compounds, especially those that contains transition metal. Okay, I will put that one, copper sulfate. Okay, so especially, write down, those with transition metals. Okay, right, let me write this in a special color. So transition metals, where can we find them? We find them between two groups, group 2 and group 3, okay? Yeah, can you add an extra remark here? When do you expect an ionic compound to be white in color? When they are formed by main group metals, okay? So those formed by main group metals, so main group metals, I'll draw a key below, okay, to show you what. Draw the outline of the periodic table first. So this is the periodic table. Where do we find the main group metals? We found them here. So group 1, group 2, they are called the main group metals as they belong to group 1 and 2. We have 8 main groups, right? Group 1, 2, 3, 4, 5, 6, 7, and 0. These are called the main group, okay? And when we talk about main group metals, that includes group 1, group 2, and group 3. Yeah, so these are called the main group metals. So main group metals. They form white compounds that dissolve to form colorless solution. Okay? Then we have the transition metals that sits in between group 2 and 3. Okay, so these are called the transition metals. For example, we have like a Fe, we have like a Cu, okay, things like these. Okay, iron, you see, is a transition metal. Copper is a transition metal. What's so special about the compounds formed by transition metal? They are often colored. Okay? But main group metals, not so much. Let's take a look at Na. This is where Na sits. This is where K sits. Okay, and then Ca. Do you remember what limestone is from the previous test? What is the chemical name of limestone? Calcium carbonate. Yes, and this is white in color, right? So it fits into this rule here. That main group metal compounds are white in color. Okay, so you have potassium, calcium, sodium. So now you know this. Ionic compounds formed by main group metals like calcium carbonate, sodium chloride. Just add a few. So calcium carbonate, calcium oxide. As long as they contain a main group metal, they are white in solid state and they form colorless solution. And then ionic compounds with transition metals like copper sulfate, iron nitrate, so FeNO32. So you see there's iron in here. Iron is a transition metal. So those with transition metals, we say they are usually colored. So they are usually colored. And they may dissolve to form colored solution. So may dissolve to form colored solutions. But sadly, the color of these ions, you will have to memorize it, okay? There is an explanation for the colors, but it's way beyond the DSE level, okay? So just put down a box here and write down colored compounds will give colored solution. So colored compound will give colored solution. Right. So now let's take a look at the ions, okay, formed by transition metals, and also, yes.
So the ionic compounds formed by main group metals do all the elements have to? Does all of it have to be main group metals?
Main group. All main group metals, ionic compounds, they are white in color. As long as it's main group, like group 1, group 2, group 3, anywhere in these three regions, these three columns, these will form compounds that are white in color. Yeah, but if you have a metal from within the transition metal region, it could be colorless. Some can be colorless though, okay? Yeah, so this is why you need to be extra careful with the wording I use here. Some, not all. They are exceptions, okay? So I don't want to mislead you. So can you put a box in here and write down? Yeah, some transition metals still form colorless compounds, okay, or white compounds, okay? So some transition metals still form white compounds or colorless solution. Write down 2 examples that you need to know. Silver, okay, ion, zinc 2+ ion. These substances, okay, they will form white compounds and colorless solution. Remember silver nitrate? Do you remember doing experiment on silver nitrate? The silver white is colored? It's not colored, right? Yeah, so that way, you know silver nitrate is colorless because it contains silver ion. Okay? Yeah, so this time we did a lab on that, right? So recall that silver nitrate, AgNO3, is a colorless solution. So that makes sense. But okay. Okay, right. So so that should make sense. Okay. Now, so just remember that silver nitrate is a colorless solution because it contains silver ion. Now we will look at some other ions, okay, that you need to know the color of, unfortunately. Don't worry, you can learn it progressively through the DSE process because in here we are just introducing you to the many colors. You will see them again, some of those ions in the later part in DSE. So this how you need to know. Now we need to look at the color of certain ions. Okay, so color of ions. First, we have iron 2+, iron 3+. So transition metals, they are unusual in that they can usually form ions with more than one charge, unlike the main group metals. Okay, so put down this remark in here. So recall that transition metals are unusual. Okay, so they are unusual in that they may form ions with more than one possible charge. Okay, so more than one possible charge. Take iron as an example. Iron, Fe, can form 2 possible ions. Okay, for example, Fe2+, Fe3+. Okay, so this is iron, and this is iron ion. Okay, so you have 2 possible iron ions. So 2 possible iron ions. They're colorless. You have to memorize it. Okay, so Fe2+ is green in color. Yeah, it will form a green solution. Iron 3+ is yellow in color or even brown, depending on the concentration. Okay, so it's like tea. You know, the more concentrated tea is the darker the color. So yellow or brown is just a matter of concentration. Then we have copper. So we have copper. So copper will form Cu+, which is blue solution. So don't confuse this with flake test. Yeah, when I say the color of copper 2+ is blue, I mean even when you're not heating it, even when it is in a compound state, it is blue. Okay, you don't need to heat it. Yeah, but the flame color of copper 2+, does anyone remember? What's the flame color of copper 2+ ion? Bluish green. Yeah, brick red is calcium 2+ ion. Okay, so calcium 2+. So put this down. Yeah, and then we have cobalt. So cobalt. So cobalt and copper, it should ring a bell because they are used in the compounds. Okay, for the test of water, test for the presence of water. What are the 2 compounds that can be used to test for the presence of water? Copper 2 sulfate, anhydrous, and cobalt 2 chloride anhydrous. Remember where we talked about that here. and hydrous copper 2 sulfate is white. But when you add water to it, it turns blue. So copper 2 plus ion is blue, and cobalt ion is pink. It's pink. Okay? These two compounds, they are important in DSC. Okay, remember that. So can you put this down? Cobalt has a symbol CO. Okay? Right. So it is pink in color. So this is pink. Can you please wake up? If not, you will have to stand up for 5 minutes. You will not. Okay, so this is cobalt, and then we have nickel. Nickel is Ni2 plus. Okay, nickel ion, I should say, is Ni2 plus. It is green. Okay, so it is a green ion here. Okay, and just when you think that only positive ions, what do we call positive ions again? There's a single word for positive ions. Cation. What about negative ions? Anions. So just when you think that only cations are colored, well, on the right we have a bunch of negatively charged ions, the anions that are colored. So we have so just when you think that we have only colored cations, so we have colored anions on the right. Okay, so here put down a bunch of colored anions. Right. So this includes MnO4 minus, which is purple. Okay, so this is purple. And then we have Cl2O7 2 minus. Right, these ions, what do we call them? Okay, can you put down the name? Put down the name of these ions. Okay, we have in here iron 2. The number 2 we write in Roman number. Okay, write it in Roman number. Yeah, the Roman number describes the charge. Okay, so if you see a 2 plus charge here, we write in Roman number 2. This will be called iron 3. This will be, as you may have guessed, copper 2, cobalt 2, and nickel 2. Okay? So you have colored cations. These ions on the right, they have very complicated names. Okay? These ones on the right, they call it anions. The first one, we call it permanganate ion. So permanganate. Don't mix up manganese and magnesium. Manganese is Mn, magnesium is Mg. Okay, so I see a lot of students mixing up Mn and Mg. They are not the same apparently. So right now Mn is manganese. It is a metal. Magnesium is another metal. The names look similar. Okay, except that they are not the same thing. Okay, so you have dichromate ion. So dichromate ion is orange in color. And then there is also chromate. So this is chromate. Why is one called dichromate when the other is called chromate? Okay, what's the difference? You see there's a number 2 in here. 2, therefore di. You don't see any number in here. Okay, you don't see a number in here. This is why it's missing the prefix di. Okay, so we just call it chromate. So these are yellow. Okay, and the least I need you to remember are these colored cations and anions. So this is the least you need to remember, the color. I don't mean that these are the only ions you need to know. These are the only colored ions that you need to know. There are a lot more ions, okay, in the chapter that you will find on the textbook where there's a table. But we will use this for our following discussion. In the lab, we can show the color of these ions by doing 2 experiments. Okay, so after you put down the color of the ions, okay, we will use that for our discussion below. Right. So the colors can be explained, but not at this level. Okay, just memorize it for now. Okay. Next up, right, we have experiments to show Number one, that ionic compounds are made of ions. So we can show that ionic compounds are made of ions. And the second thing we can show is that some ions are colored. Okay, so an experiment to show that some ions are colored. And for that, we can do an experiment below. Okay, yeah. So I'll see if I can arrange this experiment. But it's very simple. It's very underwhelming. Okay, you will not be wowed by the experiment in any way. Trust me. So first, draw this setup here. So you may have learned about circuits in like some science class. Okay, what does the longer and the shorter arm represent? The longer arm, which one is positive, which one is negative? You don't know, but you know one is positive, one is negative. The longer one is positive. The shorter arm represents the negative electrode, or the negative terminal of the battery. You have all used an AA cell battery, right? Have you? You know this is the AA cell battery. This end of the battery, you know, is positive terminal, is a positive terminal. This end is the negative terminal. In science, we don't draw this diagram. It's too time consuming to draw this. So instead, we'll just draw one line long, one line short to represent that. Other than that, they mean the same thing. This is the same thing. It just looks off, I don't know, okay? And then what do? We can connect this to two electrodes. So electrodes are rods that conduct electricity. Okay, the cheapest type of electrode is graphite electrode. So can you label this as graphite? You know graphite is in pencil lead. Pencil lead has no lead. It has graphite. So graphite electrode. Write down what electrode means. Electrodes are rods that conduct electricity. So they are rods that conduct electricity. And because of how we are connecting the electrodes, can you see that this rod is connected to the positive terminal? What does it mean? It means this rod is positive charge. Because when you're touching something positive, it makes you also positive. Okay? Yeah. This I don't know how to explain this to you, but this is physics. Okay? When this rod is connected to the negative terminal of the battery, it is made negative. Now, some interesting thing happens when you put a U-shaped tube in here. So draw a U-shaped tube below. So this is a very fancy U-shaped tube. And in here, we have put a gel with the compound copper 2-chromate. Okay? Yeah, so copper 2-chromate or copper dichromate. So maybe I will just use CuCl2O7. So this compound, can you help me put down the name? It's called copper 2 dichromate. So this part of the compound, we call it dichromate. You saw that before. This is dichromate ion, Cl2O7 2-. Why do you not see any charge in here? That's because copper 2 means Cu2+. Dichromate means Cl2O7 2-. Why do you not see any charge? That's because they cancel out. Remember, you can understand it two ways, right? You can either use the puzzle method to visualize copper 2+ as something like that. You can then use the another piece of puzzle here to represent dichromate ion. Right. And because the numbers, they simplify into 1 and 1. Therefore, you don't see any numbers at the end. You just need one copper ion and one dichromate ion. Or you can write, when you put the numbers next to, at the bottom end of each compound here, you have Cu2, Cl2O7, which simplifies into just Cl2O7. Do you get how we go from copper ion and dichromate ion all the way to the final compound CuCl2O7? Okay, right. Now, this is the compound we put in this gel. Okay, so we are putting this compound in this gel. This is the jello-like substance in here. This one, this is the jello-like substance. And on top, we are filling in some concentrated hydrochloric acid. The same acid you find in your stomach. Okay, so right now, this is corn HCl. This is a gel with CuCl2O7. Now what happens? This compound, as you saw, is made of Cu2 plus and Cl2O7 2 minus. Let me ask you a simple question. You know opposite charges attract, right? If this is a positive ion, to which electrode would it want to go to? This is where they start off their journey. So you have some copper ion and some dichromate ion here. Where would the copper 2 plus ion go? It's like they're in the middle of a crossroad. There are two paths to choose. If you are copper 2 plus ion, you're positively charged. To which electrode would you move to? Positive or negative? I hear some answers positive, some on negative. Do you know that opposite charges attract? So if you're positive, you will be drawn to the negative. So copper 2 plus, they will begin the journey here and they will move over here. And dichromate ion, because they are negatively charged, by opposite charges attract, they will move to the positive terminal. So you'll see a trail of ion movement to both sides, okay? It is as if this experiment splits the compound into two, and then the ions, they migrate to the oppositely charged electron. So draw this. You have, at the beginning, this compound in a U-shaped tube, and draw another diagram on the side to show what happens afterwards. Okay, so this is what you see before the experiment starts, and this is what you see after some time. Okay, so after some time. So you have some blue and some orange substance in here. So blue, the blueness is due to copper 2 plus ion. The orange color is due to the dichromate ion. At first, it's very difficult to see the color of the compound because like they are mixed. Okay, and then after some time, the orange color it will migrate over here. So the orange color it will move over here, and the blue color it will move over here. Okay, so you see a trail of ion movement to these two electrodes. They separate into the two different ions. Okay, so write down a very, very important principle that you're using here. By opposite charges attract. By opposite charges attract. This ion, Cu2 plus, because it is positive, it will move to the negative terminal. So because it is positive, therefore it will move to the negative terminal, which is the right hand side. Cl2O7 2 minus, because it is negative, therefore it will move to the positive terminal. This is what I mean by opposite charges attract. Is that clear? Yes. Okay? Right. A lot of new stuff to remember. Ions. Okay? I may ask you that later. Now we can go back to our discussion on bonding. We have so far discussed ionic bond and covalent bond. There's a third type of bond known as metallic bond. Okay? So, any questions so far? No. Okay? Yes.
Why do you say HCl?
Sorry?
Why do you say HCl?
Oh, why do we use HCl? Well, that's because we want, how do I put it? We want a solution that can dissolve these two ions. Okay? Yeah, and the gel serves to slow down the ion movement. It's kind of like you moving in, I don't know, like some kind of putty. Okay? So the gel slows the ions down so that we can see the movement more clearly. It's kind of like when you are seeing somebody in slow motion, you can see where they are moving. Okay, when they are moving too quickly, then you might not be able to observe the ion movement. So the gel, put that down. The HCl is just used to dissolve them, okay, and for them to show their colors, okay. But the word gel here is important. So the gel slows down the ions, slows down the ion movements, so you can see where they migrate to. Because if you don't use the gel, they will be moving too quickly to the electrode so that you can't see where they move to. They will just go over here. You cannot see that they are moving towards the electrode. Okay, you want to see the movement. Okay, to identify like the presence of ions in the So slow down ion movement so you can see their trail. Okay? Right. Next up, we have metallic bond. Okay, so we have discussed ionic bond, covalent bond. What about metallic bond now? Well, metallic bond, maybe let's do a summary in here. So ionic bond, covalent bond, metallic bond. Write down where is it found. Ionic bond is formed between metal and non-metal. So it's formed between metal and non-metal. And you will find a pair of ions. Okay, so when you have a metal atom here, and then you have a non-metal atom here, yeah, they will transfer electrons between them. So this is a metal atom. This is a non-metal atom. The metal atom will transfer electron to the non-metal atom, like that. Okay, so electron or electrons. Okay, and this will result in a pair of ions. So you'll have Na plus ion and B minus ion. Okay, so you'll have I should use a different color, sorry. So B minus ion. So that means you get so you get a pair of metal cations and non-metal anion. And where is the bond? The bond is found here. Okay, so this is known as ionic bond, as there is a pair of oppositely charged substance. Bond is a type of attraction. Okay, you will find a bond where there are two oppositely charged things. Okay. Now, the charge of the metal ion you see depends on the group number. So right now, if it belongs to group, which three groups form positively charged ions?
1, 2, 3.
Group 1, 2, 3. They form ions with charge of +1, +2, +3. Yeah, kind of boring, right? So group 1, 2, 3. Their charge will be +1, +2, +3. Which three groups will form negative ions?
5, 6, 7.
5, 6, 7. What are their charges now?
-3, -2, -1.
Yes, -3, -2, -1. We did a discussion on this, remember? So 5, 6, 7, -3, -2, -1. So that's how the group number affects the charge. So this is why I wrote A plus here. I didn't write a specific number because it depends on which group the metal is from. It depends. If you have Na and Cl, Na from group 1, Cl from group 7, then it will be Na1 plus Cl1 minus, right? Yeah, so that we learned ionic bond. We have write down transfer of electron here. Yeah, it's like transferring money. When you transfer money, you're losing money. Somebody else gain money. Yeah, in this case, the metal is losing electron. Non-metal is gaining electron. This is why only the metal will form cation. Why can't the metal form an anion? Because it's the guy giving up electrons. When you give up electrons, you must become positive. You cannot become negative. Okay? Right. Next up, we have the covalent bond. This is supposed to be just a summary, so I have to give it short. So we have covalent bond. How is covalent bond formed? Well, it is formed between non-metals only. So formed between non-metals only. Right. So you can put down, there is an atom. So this is a non-metal atom. There is another non-metal atom here. In between, they will share electrons. What is at the center of the atom? Do you all remember? What is that mass? Yeah, what is it? The nucleus. What is the charge of the nucleus?
Positive.
Positive, yes. So when two atoms share electrons between them, we have a bunch of electrons in here, you see. Yeah, so you can draw the electrons in orbits. Okay, so this is moving in shells, you see. At the center of each atom is a positively charged nucleus. Okay, yeah, I think it's best that I draw a new diagram on that, sorry. So we have, at the center, we have the nucleus. Maybe I'll just draw one proton here to keep it simple. And then we have one electron moving in order. So this is what a non-metal atom looks like. Here's another non-metal atom. What happens when they form a covalent bond? They will share some electrons in between them, right? Yeah. And do you see that inside the atoms, you still have a positively charged nucleus? Remember what I said? A bond is an electrostatic attraction between something positive and negative. You can see something positive and something negative inside this thing, known as a molecule. This is a bond. This is a bond that holds the shared electrons in position. This is why the atoms don't fall apart, okay? Because there is attraction between the nucleus and the shared electron. Same here. You can also draw some attraction here. This attraction, we call this covalent bond. So this is a covalent bond. You are seeing only one covalent bond in here, despite two like purple regions, despite you seeing two purple regions here. So you have a covalent bond. Right, this is a covalent bond. And this is by sharing electrons. Okay, so can you, when you do revision, just look at them side by side. Here, you have transfer. Somebody lost electrons, somebody gained electrons. Here, we say sharing of electrons. So they have in between some sharing. Yeah, compare and contrast the two. You have transfer, and in here, sharing of,
Oh, sir.
okay, sharing of electrons. Right, so here you have sharing of electron pair or pairs. Okay, so that's covalent bond. Now we have finally metallic bond. So let's also use the space below. This is new, metallic bond. So metallic bond is found in a single metal. So it is found in any metal. So in any metal. For example, we have sodium. Okay, so let's take sodium as an example here. So we have sodium. Right. So sodium has atomic number 11. What is the electron arrangement of sodium?
281.
281. Yes, so 281. So that means it has one outer mole shell electron. Okay, so we will draw it like this. Sodium has 11 protons. It has also 11 electrons. But there is one outer mole shell electron, you see. Okay, so let me draw 11 plus in here. And then there is 10 electrons. And there is another electron on the outside. 10 plus 1 is 11. So this is unstable right now. Okay, so sodium atom is unstable because it currently has only one outer mole shell electrons. Okay, so can you maybe draw one more circle in here? This is 2, this is 8, that is 1. Sodium atom is unstable as the outer mole shell is not full. Okay, because this is not full. Okay, so not a full outer mole shell. How can sodium make itself stable? Well, easy. It will just lose one. It will just strip off its outer mole shell electron, and instantly it becomes stable. Just watch. You have 2 electrons here now, 8 electrons here now, and you see I changed to the color green. At this moment, however, it has become positive charge. It has given up that extra outer mole shell electron, you see. So sodium atom has become a sodium ion, Na+. It is now stable because it now has a full outer mole shell. But you know that electron that sodium has given up, it will leave the sodium ion, and then it will be found here. So can you put down positive 11 here first? So this is stable as it has a full outer mole shell. Imagine what happens if you have just not just one sodium. You have many sodium atoms. Okay, what will happen? Each of the sodium atoms will lose one electron to become sodium ions. So this is what eventually happens. Yeah, I think I should move this over. On this side, sorry. Right. So when you take a look at the sodium atom, so at first, all the sodium atoms, they are very unhappy, you see. So this is sodium atom. Okay. But once they have all given up an electron, okay, so when each sodium gives up its outermost shell electron, yeah, what will happen? They will all become stable. So outermost shell electrons. But then what will they become as a result of that? They become Na plus charged ion. Okay, so they become Na plus, Na plus, Na plus, like that. Okay, what about that electron? That extra electrons that got kicked out from the sodium, it will become delocalized. Okay, so you see this sodium has given up the electron. This sodium has given up another electron. This sodium has also given up one electron. So these electrons, once they are given up by the sodium atom, they will then be able to leave their original location, and they can move around. So this electron, it can move around here, okay, and as a result of that, we call these a delocalized, meaning they are not restricted to the original position, okay. Delocalized sea of electrons. I did not make this up myself, okay, this is an official term. We call this a sea of electrons because there are many electrons, each sodium giving up one of their outermost electrons, and they will join. All these electrons, they will join to form what we call a delocalized sea. Delocalized because they can move around readily. And it is because of the delocalized nature of these electrons that metals are very good. Are they good conductor or are they good insulator?
Conductor.
They're good conductor, okay? So we'll be able to explain this feature of metal, okay, down below. Yeah, so this is how metallic bond is formed. Where is the metallic bond? You see there is attraction between the something positive and something negative. So anytime you see something positive and something negative, you have a bond. So therefore you see a bond everywhere in here. So finally, can you just reduce this diagram into a bunch of positive ions and some electrons? Okay, so you have the electrons in here. Yeah, so try to draw as many electrons as you have ions. Because if you have one particle in greater number than the other, it will mean that the whole structure is not neutral. So you need to show, you see I drew 6 blue ions, the ions here, which is why I also drew 6 electrons here to balance out the charge. The overall metal is electrically neutral, so the number has to match. And can you draw this attraction here? We said where there is oppositely charged things, okay, there will be attraction, okay. So this attraction we call it metallic bond. So this is metallic bond. A bond is an attraction, okay. So you have a bond here called ionic bond. You have a bond here called covalent bond, and over here on the right you have a bond called metallic bond. So metallic bond is found in metals. Covalent bond is found between metals. Ionic bond is found between metals and non-metals. So far, any question first? Yes, yeah, you can finish copying this down first. Let me just separate these things, okay? So you have ionic bond, metallic bond. So here put down the definition, okay? So help me put down the definition. So bond, so a summary on bonds. Okay, so summary on bonds. A bond is an electrostatic attraction. So you can write down bond here is the electrostatic attraction. You know electrostatic means between positive and negative. When you have something positive attracting something negative, the attraction between them is called an electrostatic attraction. Okay, so Let's dumb this term down a little bit. It means the attraction between something positive and negative. Okay, so between something positive and negative. That's electrostatic attraction. Between, right, so this is a table. So I want to draw a table in here. So we have ionic bond, we have covalent bond, we have metallic bond. So it is the electrostatic attraction between cations and anions for the first one. Okay? And covalent bond is the electrostatic attraction between the nuclei. Where are the nuclei? These are the nuclei. I use plural because there are always two nuclei
Yes.
when a bond is formed. You cannot form a covalent bond when you have just a single atom. A bond has to be formed two parties. Like just like marriage, you cannot marry yourself to marry somebody else. Okay. So this is a pair of nuclei. Okay, plural. So they are positive. Make sense, right? And then you have shared electron pair bracket S. Because we can have a single bond, double bond, or triple bond. Sometimes you see one pair of electrons here. Sometimes you see two. Sometimes you see three. But then it doesn't change the fact that it is still a bond formed between the shared electron pairs and the nuclei. I don't care how many electrons you put in here. As long as there are electrons here, this part will be negative. And this negative group of electrons will be drawn to the positive nuclei. Okay? Right. So, what else? We have also metallic bond. Can anyone tell me what do you think makes up the metallic bond? If the ionic bond is the attraction between cations and anions, if covalent bond is the attraction between positive nuclei and shared electron pairs, let me write down shared electron pairs. What about metallic bond? What is metallic bond the attraction between? Zero electron and what do you call positive ion? Cation. So write down is the attraction between cations and the localized sea of electrons. So there is something in common between all these bonds, is that there must be a party that is positively charged and then another party that is negatively charged. Okay? As a bond has to be an attraction between these parties. Okay? So you have, is that clear?
Yes.
I know this is a very difficult concept to follow, okay, at first. The localized sea of electron. Oops. So you have, this is negative. And so is this negative. Is that clear? Yes? Okay? Right. So we have discussed three types of bonds now, okay? Now, let's move on and discuss, okay, the next part is the structure, okay? So what are ionic compounds, covalent compounds made of, okay? So we have bonding and structure to create like a new title, okay? So bonding and structure. So we have just learned three types of bonds, and we are about to learn four types of structures. Okay, so we have just learned three types of bonds. Okay, so three types of bonds: ionic, covalent, metallic. Okay, so ionic, covalent, and metallic. And we are about to look at a bunch of structures. Okay, so bond is just telling you how atoms attract, how things are joined together. Structure describes how they are like connected. Okay, what shapes, okay, do these structures have? Okay, so we will now learn four main types of structures. Okay, so four types of structures, which are related to the bonds. Okay, first, ionic bond would lead to the formation of what we call giant ionic structure. So giant ionic structure. Yes.
The structure of what?
Structure of substance. Yeah, so yeah, let me be clear. Yeah, so 4 types of structures of substance. You know, in chemistry, we deal with substances. Like salt is a substance. Water is another substance. Okay. By substance, I mean pure substance. I don't mean impure substance like air. Okay. So every pure substances can be classified into one of the following 4 structures. Okay, so that's a good question. Structure of what, right? So structure of pure substances, e.g., water, e.g., diamond. Okay, you know, as long as you have a pure substance, you can classify them into one of these 4 categories here. Okay, we have giant ionic structure. I know the book has a 5th one, but that one I consider it as part of the other structure. Okay, don't worry. So we have giant ionic structures. We have simple covalent substance. So simple covalent substance. We have giant covalent structure, and finally giant metallic structure. So giant covalent structure and giant metallic structure. So how are the bonds related to these structures? Okay, so we'll look at it now. But first, I need to tie these together. Ionic bonds are what forms the giant ionic structure. Covalent bonds can form either, okay, the simple covalent substance or giant covalent structure. Metallic bonds will form giant metallic structure. Makes sense, right? I mean, ionic bond, you will not tie it to giant metallic structure, right? You don't even sound alike, okay? So ionic has to be related to something ionic. Covalent has to be related to something covalent and metallic. Yeah, same likewise, okay? Now, let's take a look at giant ionic structure first. Okay, we already saw how the bonds are formed. We need to link into the structure now. So giant ionic structure. Have you ever wondered what is this the structure of table salt like? If you look at a grain of salt, you will see that it is a crystalline solid. What does crystalline mean? It has a very sharp edges. You know, salt crystal. Have you taken a close look at salt crystals before? You know they have sharp edges. If you look at them under the microscope, this becomes even more apparent. So why is that? That's because they have what we call a lattice structure. So can you put down all ionic compounds? So all ionic compounds, e.g., NaCl, KCl, MgO. Ionic means metals and non-metals. There has to be a metal part and a non-metal part in these compounds. Okay, so all ionic compounds, okay, have a lattice structure. So learn a new word today. Lattice. Yeah, a lattice means it's not like the vegetable lettuce. Okay, yeah, but it's a lattice structure means a regular arrangement of things. Okay, so a regular arrangement of cations and anions. So formed by cations and anions. Right. I know this is very difficult to wrap your heads around, which is why now I wanted to draw a tablespoonful of salt. So you have salt in here. When you zoom in really, really close onto a single grain of salt, you see this. It looks like a cube. Why does the salt grain have a sharp edge? That's because when you look inside, you will really find, well, this you can try your best to draw. If you really cannot draw it, it's fine. Just refer to my notes. Yeah. But this one here, you see you have a bunch of positive ions surrounded by negative ions, like that. So this is a very tidy arrangement of ions, you see. On the side of each positive ion, you get a negative ion. And this is just the top level. Then you have another bottom level below that looks exactly identical. And then the middle level in here. So you have a middle level here, which has the position of the ions reversed. So you see at the corners, there used to be middle level is just reverse the positions. So you have negative, negative, negative. You won't be asked to draw this, trust me. But I want you to look at the diagram and tell me what you see. Between any two like charged ion is always an oppositely charged ion. Yeah. So this is to show that the ions, they are really like a pack in a very, very regular arrangement of ions. Okay, so this structure is why table salt has sharp edges. Okay, this is, you can see sharp edges on the side. Okay, so this arrangement of ions ensures that, okay, they have a very sharp edges. Okay, so can you put down, we'll put this diagram here as well. So you have table salt. So table salt is sodium chloride, the ionic compound. And here you have a salt grain. And when you take a very, very close look at this salt grain, you will find that it looks like a box. Inside this box, you will find many ions of opposite charges, okay, like that. So you will find ions, I should show it more properly here. Yeah, like that, okay. So you will find ions of oppositely charged. We call this a lattice. So this is an ionic lattice. Where are the ionic bonds? You'll find ionic bonds here, here. In fact, everywhere. Okay, between any two pairs of any pair of oppositely charged ions, you find ionic bond. So ionic bond is everywhere. Okay, in the structure. So this maintains the structure. So ionic bond is found everywhere within this structure. So is it clear what it looks like inside salt? And it's not just NaCl. Yeah, if it is NaCl, if this is NaCl, this will be Na plus ion. You don't just see one Na plus ion, you see. In table salt, you have hundreds of thousands, maybe even millions, okay? Maybe millions, it still doesn't cut it, okay? It should be more than 1 million, okay, sodium ions, and more than 1 million chloride ions in here. So these are chloride ions. There are many. They are arranged in this very tidy arrangement. And this structure is just like a snapshot of what you will find. It extends in 3 dimensions. Yeah, it is only a slice of the entire structure you find in sodium chloride. The real structure is many, many times larger than this. Okay, and you have expect 10 billion times more sodium and chloride, and they all packed in this very tight arrangement called the ionic lattice. And what kind of properties can we think of for giant covalent, giant ionic structures? So can you put down these properties on the right? So properties of giant ionic structure. So properties of giant ionic structure, beginning with number 1. They have high melting and boiling point. Have you tried melting salt? Yes? No? Yeah, I don't think you can melt salt at home because salt has a melting point of 1,500 degrees. Yeah, so that's high compared to the melting point of water, which is just 0 degree, right? One is 1,500, one is 0. They certainly have very high melting and boiling point. Okay, so write down high melting and boiling point. Why is that? So this is because the structure is maintained by many strong ionic bonds. So it is maintained by many strong, the keyword here is strong. So strong ionic bonds. So the bonds hold the ions in position. Okay? When you melt something, what do you mean? It means you need to separate the particles, right? So if these ions, they are, do you remember learning melting in Form 1? So this is solid. Melting means you're turning a solid into a liquid. So you have a solid here into a liquid. So this is what we call melting. In the case of ionic compound, it will be like turning these ions that are tightly packed into ions that can freely move around. Yeah, what do you need to break if you want to free the ions?
They're one.
Yeah, a lot of ionic bonds. We need to use this specific word here. It's like they're chained up by these strong forces called strong ionic bonds. Because they are strong, it will take a lot of effort, okay, for you to melt it. So this is the first property of ionic compound, the high melting and boiling point. And just put down one more thing in here. It is because of them having high melting and boiling point that they are solid at room temperature. Yeah, they are always solid. Okay, ionic compounds are solid. So because of their high melting and boiling point, therefore they exist as solids at room temperature. So now you know something. The property of salts, for example, the melting and boiling point, or its state, is related to the structure. The structure called giant ionic structure, which in turn is probably can be explained by the ionic bond. Okay, so we'll pick up from here. And I have your homework, okay, with your names written on it. Just pass it on to the front. I'll collect it from the student net.
Can I submit it tomorrow?
Yes. If you don't have it now, you can hand it in tomorrow, the latest. The latest. Okay?
एक घंटा 13 मिनट Forgot. Thank you.